to, you know, about 1,000 processor supercomputer with all of your data in it ready to go. So I think that sounds neat, but you know what? The way science is done these days is with collaborative teams all over the world using the network to stitch themselves together, and one buzzword is called grid computing, or computing in the cloud, or science in the cloud. There's all kinds of buzzwords around it. It may be buzzwordy, but that's how science is done. So if we're going to start teaching kids, future scientists, about science, why don't they learn in the context of the way science is done? So that's the idea. Everything we do, with one exception, which is something we licensed in, is public domain, fully available. There's absolutely no commercial agenda behind this. We've already given our designs away to a number of places. And we expect to rewrite our software about 20 times. We have 9 full-time software engineers, 5 of which are degreed computer scientists, and the other 4 of which are degreed astronomers, but they're the kind of astronomers who've turned into computer scientists. So a very large team working on the software, and we anticipate rewriting it 4 or 5 times till we get it right. Okay, I'll skip that one. Oh yeah, this central cluster, this supercomputer, we're not building a bunch of telescopes. In our vision of this is a telescope. You go to LCOGT, you state the observation you want, and it happens where it should happen at the right time. And the notion that it's XYZ telescope, as a user, you're blind to. Now, we're not really blind. We're not trying to hide anything. But we're trying to get everybody to come in the same way so that we can schedule it and get the most throughput from it. And since we bought it, we get our way on that one. This has been a big battle. Every time I go to a conference of techno people, they get all excited at the problem of building a distributed telescope where all of these telescopes talk to each other and simultaneously they all figure out how to do the right thing. And since my closest model of that behavior is the US Congress, I think we've decided we're not going to do it that way. Benevolent dictatorships really have their purpose in life. And so one computer can sit there and reevaluate the schedule, you know, continuously 24/7 and update it once a second. So that's how we're going to do it. Solve the simple problem first. Education time, the way we think of education time is, for instance, the Falks Telescope Project will revert to Dr. Falks. He can run his project as he sees fit. He gets a certain amount of time on the telescopes with a certain set of preferences. They can do their own thing. They don't have to live by our rules. They can do their own education thing. The Hawaii group has their own education vision. They get to do it. And all of our host observatories want time on our telescopes, and they've all told us they want to turn that time around and provide it educationally in their countries. Although South Africa, where we are, I was really floored. And I said, well, who do you want to serve with the education time? And they said, all of Africa. So they have a very great vision. And we said, fine. And then we said, well, now, what do you want to do? How do you want to develop this program? And he says, oh, well, we'll just use your program. So beware of what you ask for, you may get it. So the interesting thing is, how do you support stuff like that in schools with limited bandwidth? And how do you do it in multiple languages? And the answer is use the Google Web Toolkit and use a central supercomputer here to make all that work right. So that's how we're doing all this. We'll skip that. Okay. Our philosophy is the most important science always wins. That's not to say that education is not as important as science. But if a star is exploding in our galaxy and we catch it early and we get all our telescopes on it for 4 or 5 days, that is a scientific coup of huge magnitude. So we want to reserve the ability to do those kinds of things. And the data will all be public for everybody to analyze, so that's no problem. Okay, I'll skip that. Okay, we're moving along. We're deploying this summer. By the end of 2011, we will be up and running with the whole network, maybe with one site left. So what's going on with education to close the talk? Circa next fall. What's different? You start with experience science, using a system that scientists use. And then if you're interested and you follow through, you can grow into using the system with real scientists and doing research in a global grid environment. And that's what we are going to deliver. And we think that will result in junior colleges and high schools and many other smaller colleges that don't have big physics departments all of a sudden being able to play on the world stage with the best observatories in the world. And so I think of it as there are 10,000 professional astronomers in the world, people who say they are astronomers and whose paycheck sort of comes from astronomy. This is different than, say, folks at JPL who are doing something slightly different. But we'll think the hardcore astronomers that kind of look through telescopes, except nobody does that anymore. And they're smart people. But what if there were 50,000 dedicated grad students and junior college students and high school kids and kids in small colleges all over the world, or adults in small colleges all over the world also doing this? So that can result in an enormous expansion of creativity and of innovation and of ability to go deep on some things, which is sort of what we hope we can accomplish. So there you are. Thank you.
Being in the astronomy education business for quite a few years, I know the reliability of telescopes. I know that when they're used over and over and over again, they just don't hold up. And you showed us a Meade, I think it was what, a 16 or 18-inch telescope out there that didn't look anything like a Meade telescope anymore. That 0.4 meter you were showing here. But what's been your biggest problem with reliability with that type of thing? As far as keeping it going for a long period of time?
Well, the biggest reliability problem has been teaching the engineers to ask the question, how can this work for 20 to 25 years without failing? That's not an ordinary engineering question,
no,
unless you're building satellites. And so the answer to that is an absolute fanatical commitment to understanding the parts you're using, to very precise design, to, in the case of machining that is just, at the state of the art, electronics that's designed with extreme conservatism, and software that's built with a philosophy that every conceivable thing that can go wrong is going to go wrong, and you have to somehow work your way around it. So it's very intense, detail-oriented engineering. And to be fair, I haven't said money is no object, because money is an object. We could spend too much money and then not be able to do this because there's a finite endowment. But what I have said is that don't be cheap, make it work. And when you're building tens of thousands of something or 1 million automobiles, the issues of cost of materials become very real. But when you're only building a one-off thing like we're doing, the cost of materials, whether it's 8 million or 15 million, is not a big deal, but the difference in quality